So I'm going to start a series on classical mechanics and the theoretical minimum. And so uh, it's just what the title says. I'll try to be as minimum as possible while discussing um, about the classical mechanics. Now, this series would be uh, highly based on the book of the same name by Leonard Susskind and George Hrabovsky. So yeah, so this is the book, and so yeah, the most credit goes to the book and the authors. And Leonard Susskind is famous for this series of books, the theoretical minimum. So he has the same books on quantum mechanics and other subjects. Now, why exactly? So now I'm a software engineer, and my interests are in AI. So why am I picking up this subject in the first place? So well, let me just start scrolling. So like why the reason? So why study this at all? Like, this doesn't have anything to do with what I'm studying. Or let's say you're just I mean, so the audience for this series would be literally anyone interested to know about classical mechanics. So now, yeah. So now, why study? Basically, physics uh, must be studied by as many people as possible. Uh, it literally is the fundamental truth. So if there were any objective truths, that would be physics. Elon Musk says it. Physics is the only law, and everything else is a recommendation. Elon Musk, not just Elon Musk, like many pioneers of this century, they all suggest to study physics. It's quite important, and there's a lot of fundamental truths in it that you cannot find elsewhere. So, for example, biology and chemistry and everything, basically, they are all based on the objective truths uh, that are present in physics. So you can go on to say like maths, but let's not go that much deep into it. Let's just say that physics is the law, and speed of light and all those constants, the quantum mechanics and all those. So basically, physics is the truth. So physics, it's quite important. So in classical mechanics is just one part of physics, and this is why we're studying it. It's quite important. I mean, I learned. I mean, even though like I'm studying about artificial intelligence and other subjects, I got quite some relatable laws here. So yeah, you should. So yeah, and again, this is not even like the deep course study. This is just the theoretical minimum. So this should not be. This should only be helpful and not otherwise. And and as always, it's always recommended to study more stuff than just your field. That's what the legends do. Legends, anybody who is famous in their fields, just look at them. They just don't study, or they're not narrowed down to like whatever is in their field. So they always go further, and they study broadly and deeply. So that's why studying it. So going to classical physics. What is classical physics? So what is classical mechanics? Now, as I said, the textbook, this entire course is based on the textbook. So I will be referring the textbook once in a while. So it might take like a little bit of time making this video. So uh, maybe pausing for a while to go through the book. And as always, like like pretty much all the videos on my channel, all of these videos are just made for uh, my own explanation, and if it is helpful for anyone else, that's a big bonus to me. So, and yeah, and I also focus on the fact that somebody might hear this. So while I'm focusing on myself, I'm also making this hoping that someone else as might hear it as well. So, and so what is classical physics? Classical physics includes Newton's equations for the motion of particles, the Maxwell Faraday theory of magnetic fields, and the Einstein general theory of relativity as well. So more than just specific theories of specific phenomena, and the, it is a set of principles or rules and underlying logic that governs all phenomena for which quantum uncertainty is not important. So anything where the quantum uncertainty is not important. So let's say that like anything where anything where quantum uncertainty is not important, you can call it as classical mechanics. So this is literally like all the physics that is applicable size larger than the quantum world. And you can also say you can also add like black holes as exceptions because none of the science really matters there. So classical mechanics is broad, so you can say that. So it's basically like broad space, broad thing where except for the small, except for some holes like the quantum and the black holes and such. Now, so what is now the job of classical mechanics is to predict the future, and so the famous 18th century physicist Pierre Simon Laplace laid out. He said the same thing. So in classical physics, if you know everything about a system at some instant of time, you also know about the equations of how the system changes. Then you can predict the future. Now, uh, two important aspects of classical physics is that they are deterministic and they are reversible. Deterministic means that the given that given a set of equations and variables, you can accurately determine what the result will be. And even if like one of the variable changes, you can still determine the result. Reversal means that the process can be reversed, and not the process, at least with the equations, you can tell the state of the processes, what happens when the state is reversed. So classical mechanics exhibits these two properties: deterministic and reversible. And let's just say, like in simple dynamical systems in this space of states, let's take a collection of objects, particles, fields, waves, whatever, and call it a system. Uh, a system will have, let me take a space. Let's say this entire space is like a system, and we'll have two states. One is heads, and the other is tails. Now, in classical mechanics, we assume that the systems will evolve smoothly it means continuously. That's how the real world is, right? I mean, the real world is like analog. It's not digital. Things move smoothly, continuously. Things don't move like things move like this. Like if you were to plot the speed, position of any object, this is how it moves. And it's not like jittery. It's not like pixels level. So it's not like block. So uh, this is how it moves. And so classical mechanics, we assume that things are continuous and not in a stroboscopic manner. Stroboscopic means uh, like a strobe light. Like if you were to move like a strobe light, you would see them like in discrete lights. So that's not how it is. So the classical mechanics is continuous, not discrete, not discrete. Now the system that changes with time is called dynamic. So classical mechanics is also dynamic. Obviously, it's not static. No system, not many systems are static. Any system that's static would be something that would be taken for like just theoretical assumptions or experiments. And yeah, so the next topic that we can talk about would be about the dynamicity of states. I mean, if there are like more than one states, what would happen is that you can move from one state to another. Let's say there is 1, 2, 3. So this can move here. Let's say and this can move here, and let's say this can move here, and also yeah. So this is like a dynamic state. This is a 6-state system, and now we can say this is like law one. I can just imagine like I mean I can just say that this is a one dynamic law one. So and that will be just like a if example. Let me erase whatever I explained improperly, so that we don't get confused here. So far you learned that classical mechanics is deterministic and reversible, it's continuous, and it's dynamic. So next we will go to this topic that is the minus first law. So we know that the there are a lot of first laws, second laws, and if you were to call like the two most biggest, the most important laws ever, that would be, I mean, the thermodynamic laws, of course. So laws of thermodynamics, like thermodynamic law one, thermodynamic law two. So thermodynamic law one, which states that energy shall neither be destroyed nor created. It can neither be destroyed nor created. And second law states that the entropy always increases. Entropy or chaos always increases. So don't worry about the details of this law. So for now, just know that these are the. I mean, in case you're not aware, for now, just know that these are the two most famous laws. And there's also like another 3 laws by Newton, the laws of motion, and there's even a zeroth law of thermodynamics. So which is so let me just So zeroth law states that if two systems are A and B are each in thermal equilibrium, then the third system C with the third system C, then A and B are also in thermal equilibrium with each other on the basis of different temperatures and usable properties. So it is also a zeroth law. So if A and B are with thermal equilibrium, then it implies that A and B are also in thermal equilibrium with each other. So that's just a zeroth law. Now we want to establish one more law that we call the minus one law. That's what is discussed in this book, which is that there must be one arrow to tell you where you're going and one to tell you where you came from. Let's say there's a system of states like this: 1, 2, 3. This is the system of states. 2 goes here, and there is an arrow like this. So if you did not have, if arrow like let's say the system was like this, and the state goes from 1 to 2, and then from 2 to 3 it keeps jumping. Now where did the state 2 come from? We cannot tell that from this system. This system is flawed, or our observation of it is flawed. There's no way to tell where it came from, so it doesn't make sense. So we better have like another law called so basically it's irreversible. This is not reversible. So that's what the author is trying to say. There must be one arrow to tell you where you're going and where you're coming from. So the rule that dynamic laws must be deterministic and reversible is so central to classic physics that we sometimes forget to mention it for teaching the subject. In fact, it doesn't even have a name. We would call this the first law, but unfortunately, there are first two laws: Newton's law and first law of thermodynamics. There's also zeroth law of thermodynamics. So we have to go to the minus first law, gain polarity for what's the most fundamental of all physical laws, the conservation of information. So, okay. Yeah. So this is conservation of information. That's the law, minus one law. And yeah, so that's one thing to know about dynamic systems. And we can also have dynamic systems with infinite states. So this is a dynamic system of finite states with only 3 states. It could also be cyclic laws, cyclic systems where there is a cycle in the system. There's also limits on precision, obviously. Like if you want to say like the position or the velocity, you can only go so deeper with the instruments. So that's one topic discussed. And now, even though now there is a distinction here, so we say that the system is like deterministic and reversible. Now it is in the context of how many things we actually know in the initial time. So let me take the most famous one of the most famous topic that's called the three-body problem. There's a very famous novel and Netflix. I'm not sure if it's Netflix or Hotstar or Disney, but there's a famous TV show of the same name called Three Body Problem. But yeah, I mean it is related to the physical, the law and the phenomenon in physics. But I'm not sure how much they delve into it. But anyway, so the three body problem says that basically when you have three bodies, so we are still in. So remember that we are still talking about classical mechanics here. So if there are three bodies, okay, uh, so if you have to predict the problem of the motion of these three bodies, it would get so complicated that it would become almost chaotic. So there's this problem of chaos as well. So deterministic, but there could be chaos. So this is called as somewhat. So if there are only two bodies, it's much easier to to find their motion in 3D space time. Even in 4D space time, if you have to include time. But if there are three bodies, like how they interact with each other, it becomes so complicated. Even though the system is deterministic, even though there's only finite number of bodies, it becomes impossible. It becomes almost impossible. So even with familiar formulas and everything, it becomes what is known as deterministic chaos. So because it lacks any formula to find the thing for three bodies. So any tiny changes in initial positions, velocities cause vastly different unpredictable long-term outcomes, unlike predictable two-body problems. So there's another aspect called also predictability. So can you predict it or not? So it all depends on the deterministic, how deterministic is it, or how chaotic is it. So and so uh, basically this is because of complexity involved, and we just lack any the amount of resources to predict this. If you had a like a Turing machine, or like a if you had a theoretical computer which had like infinite amount of resources, uh, this is no big deal to calculate it. So it would, in theory, would be able to predict the motion of these three bodies. But yeah, so this is called deterministic chaos. So this is not infinite. This is not uh, undeterministic. It is deterministic. It is in theory predictable, but how much can it predict? That's the question here. So it can't predict much. So uh, yeah, so that's another concept here, and and that pretty much completes the first chapter, which was introduction to classical physics. Yeah, so that's what that was. So nature of classical physics. So now it is going to like a brief interlude into mathematics, but we will try to cover it in a different series of videos. So we won't get into the interlude, the mathematical interlude parts of this book, because let's have focus on what we're trying to do, and it may take a lot of time. So that's about it. In the next video, we'll go to the second chapter.